Top 4 things you should know about quantum physics. The quantum world is lumpy. The quantum world has a lot in common with shoes. You can't just go to a shop and pick out trainers that are an exact match for your feet. Instead, you're forced to choose between pairs that come in predetermined sizes. The subatomic world is similar. Albert Einstein won a Nobel Prize for proving that energy is quantized. Just as you can only buy shoes in multiples of half a size, so energy only comes in multiples of the same quanta, hence the name quantum physics. The quanta here is the Planck Constant, named after Max Planck, the godfather of quantum physics. He was trying to solve a problem with our understanding of hot objects like the sun. Our best theories couldn't match the observations of the energy they kick out. By proposing that energy is quantized, he was able to bring theory neatly into line with experiment. J.J. Thomson won the Nobel Prize in 1906 for his discovery that electrons are particles. Yet his son George won the Nobel Prize in 1937 for showing that electrons are waves. Who was right? The answer is both of them. This so-called wave-particle duality is a cornerstone of quantum physics. It applies to light as well as electrons. Sometimes it pays to think about light as an electromagnetic wave, but at other times it's more useful to picture it in the form of particles called photons. A telescope can focus light waves from distant stars and also acts as a giant light bucket for collecting photons. It also means that light can exert pressure as photons slam into an object. This is something we already use to propel spacecraft with solar sails, and it may be possible to exploit it in order to maneuver a dangerous asteroid off a collision course with Earth. Without it, the sun wouldn't shine. The sun makes its energy through a process called nuclear fusion. It involves two protons, the positively charged particles, in an atom sticking together. However, their identical charges make them repel each other, just like two north poles of a magnet. Physicists call this the Coulomb Barrier, and it's like a wall between the two protons. Think of protons as particles, and they just collide with the wall and move apart. No fusion, no sunlight. Yet think of them as waves, and it's a different story. When the wave's crest reaches the wall, the leading edge has already made it through. The wave's height represents where the proton is most likely to be. So although it is unlikely to be where the leading edge is, it is there sometimes. It's as if the proton has burrowed through the barrier and fusion occurs. Physicists call this effect quantum tunneling. It stops dead stars collapsing. For this one, please check out my supernova video in order to understand more. It helps us characterize stars. Danish physicist Niels Bohr showed us that the orbits of electrons inside atoms are also quantized. They come in predetermined sizes called energy levels. When an electron drops from a higher energy level to a lower energy level, it spits out a photon with an energy equal to the size off gap. Equally, an electron can absorb a particle off light and use its energy to leap up to a higher energy level. Astronomers use this effect all the time. We know what stars are made of because when we break up their light into a rainbow-like spectrum, we see colors that are missing. Different chemical elements have different energy level spacings, so we can work out the constituents of Sun and other stars from the precise colors that are absent. I recommend you to subscribe my channel and press the bell icon for more awesome videos like this.